Hello everyone. So today we're going to start on 11.4. 11.4 talk about very important and very basic application of a second order differential equation called oscillation. So what is an oscillation? So imagine the following. Imagine that we have some kind of tube, and inside this tube we have some kind of piston. And the piston is connected to a spring system. And the whole thing is inside some kind of fluid, which could be just air, but it could be some other fluid. And imagine the following. This piston have an equilibrium position where we're going to define it to be the position 0, which is called the equilibrium position. And what happened is if this piston move forward or backward, which we define one way to be a positive direction, it really doesn't matter which way we define it, and one way to be a negative direction, it will create some kind of displacement. And then when it gets displaced, the spring would exert some kind of force onto this piston to try to move it back into the equilibrium position. At the same time, the fluid provides some kind of resistance of any movement at all on the piston. Therefore, create some kind of dynamic here that we can try to examine. So that's would actually result in a second order differential equation. Now, I know my picture is not very good, so if you want to see a better picture, it's actually in your textbook, page 351, figures 11.3. Will give you a much better picture of what I'm trying to draw here. So the idea is to try to understand what's happening here. So in this system, they are basically three forces that affect the piston. So what are these three forces? So before we define these three forces, let's define the following. We go define X to be the displacement from the equilibrium position at any time t. So therefore, our X, technically speaking, is what we call X of t, our displacement function. So what are the three forces that actually being applied? So the first one is the following. The spring actually exert a force proportion to the displacement. Displacement. And that's basically what you probably remember learning in physics called the Hooke's law. So what does the Hooke's law state? It's basically saying that the force exerted by the spring is proportion to, meaning a constant multiple of the displacement, but it always go in the opposite direction of the displacement, because as you have a positive displacement, the force will want to push it back toward the equilibrium position, which requires to move in the negative direction. If you have a negative displacement, then the spring will want to exert a force that push in the positive direction to move you back toward the equilibrium position. So therefore, we can define this force to be force, capital F, spring, which is equal to negative hx, where h is called the Hooke's constant, and h has to be greater than 0. Now, also something very important to understand is that notice that what I'm putting down is not a vector. Okay? And why is it not a vector? In this case, what we're talking about is that we're talking about an object that's only moving in one direction, forward and back. Okay? Therefore, it's very similar to what you probably remember learning BC calculus called motion along a line or rectilinear motion. Okay? Where we do have a direction, but the direction only simply indicated by a positive or negative. Okay? So in this case, we have a negative direction or opposite direction to whatever the displacement is. Yes, the negative is very misleading. It's actually read opposite to the displacement. 2. When the piston travels through the fluid, the fluid will offer some kind of resistance based on what type of fluid it is. Even if it's air, and if you move fast enough, you will still experience resistance. And that resistance is often a frictional force that is proportional to the velocity of the piston. Now, and some of you probably noticed the word proportional. Proportional to the velocity of the piston. The key here is the word proportional, because the word proportional means constant multiple, and therefore allow us to actually keep our differential equation having constant coefficient. And remember what I told you, that is extremely important because it makes the differential equation a lot easier to do. So even though in some cases these might not technically speaking be constant, it might vary slightly, but we will actually treat them as constant just to make the math easier. And then eventually, if you learn more math, then yeah, it's hard to believe that there is more math for you to learn, then you might learn how to deal with that when they're not constant. So this force, I'm going to call them frictions force. Oops. Is once again directly opposite to the movement, meaning if you're moving forward, the resistance actually want to push you backward to slow you down. So therefore has to be negative k, but it's proportional to the velocity, so therefore it's proportional to dx over dt. And of course k has to be a positive constant. Alright, good so far? And that was the last thing that's involved. The last thing is the following. The piston might have some kind of external force that move it. Okay, an external force let's just say F external equal to some function F may be applied to the piston. And if it does, then definitely have to be calculated within the system. And so now that we have these three forces all act onto this piston, we can now define what is the net force. So the net force will basically equal to the sum of these three forces add together. F external, plus F friction plus F spring. According to Newton's second law of motion, the net force should be equal to mass of the piston multiplied by the acceleration. So therefore, should equal to m times d squared x over dt squared, which is the second derivative of the displacement, which is the acceleration. And that should equal to the external force F minus friction, which is k times dx over dt, minus the spring, which is hx. And now what I'm going to do is kind of rearrange it into a nicer form. So this equation actually turns into this one. mx double prime plus kx prime plus hx equal to f. Notice what we have right here is a second order linear constant coefficient. Oops. And assuming that f is not zero, non-homogeneous differential equation. Lucky for us, we just learned how to solve non-homogeneous constant coefficient differential equation in 11.3. So now we can try to figure out what the solution to this equation is going to be. So this equation basically describes the oscillation of movement. This differential equation. And of course, I know we derived this equation from the piston moving with a spring, but it can actually be used for almost any kind of oscillation. This differential equation basically describes the simple motion of an oscillation. And what we're going to try to do is to try to figure out how would this differential equation look like based on various value of m, h, k, and f. So we will try to investigate just to try to understand various assumptions of, well, m is the mass, so that really can't really do much. But we go try to do different assumption of h, k, and f to see their effect on the solution to this differential equation. Now, when I say various value, basically what we're looking for is try to understand what happened to their value relative to other value. Like what happened to h and k, if h and k are the same, or if h are bigger than k or less than k. Remember, h and k both have to be positive value. Okay, but they could take on many different value, infinite number of different value. And when you have a different value for h and different value of k, it will create a different dynamic for the oscillation. And that's what we're trying to figure it out. So let's start our first discussion on probably the most basic oscillation, which is referred to as harmonic oscillation. So what is called harmonic oscillation? Harmonic oscillation is when there's no external force on the piston and there's also no resistance, meaning imagine this whole thing happened in a vacuum. So our first assumption is that there is no external force on the piston and no resistance from the foot. Okay, and this basically represents what we call the ideal scenario. And if you think about it, you actually kind of know from a physical standpoint what would happen in this case. Okay, this is called a harmonic oscillation, or often referred to as free oscillation. And if you think about it in this case, now here's the interesting thing is that to think about what we're doing here is to try to create a mathematical model that kind of describe what is actually happening. So therefore, our model should make sense based on the physical evidence of what we observe. So think about in this case, if you do have what we call a free oscillation, meaning there's no resistance, there's no external force, then what would happen is that the oscillation should go on forever. Because conservation of energy dictate that if there's no external force to introduce new energy into the system, there's no resistance that would lose energy in our system, then the system should just keep going on forever. The oscillation should go on theoretically forever. So let's see if that's the case. So what does it mean when I say there's no external force? Well, no external force implied that our function f of t is our zero function. And no fictions indicate that our constant k must equal to 0. Therefore, the entire friction force would drop out from our equation. So when that happens, we would form our new equation. Our equation m x double prime plus kx prime plus hx equal to f will then turn into this equation, m x double prime plus hx equal to 0. And guess what we have? A homogeneous equation, which is nice. I'm also going to take one extra step. Since I know the mass of the object has to be a positive constant and cannot be 0, because if it's 0, then we have no mass. That means we don't have a piston. Then this whole thing is imaginary. So, assuming the mass m is not 0, I can go divide out the m and say this is my equation. That is our homogeneous second order differential equation. So now comes the big question is, what is the solution to this differential equation? Well, since homogeneous, we go use our characteristic root to solve for it. So this equation, x double prime plus h over m x equal to 0, basically turn into r squared plus h over m equal to 0. That is our characteristic equation. Therefore, tell me that r squared must equal to negative h over m, and therefore r must equal to, notice that h is positive, m is positive, therefore negative h over m must be negative, and result in imaginary roots plus or minus I radical h over m. And based on that, we now should be able to write out our solution. Our displacement function, x of t, should equal to c1 cosine radical, h over mt plus c2 sine radical h over mt. So that is our free oscillation differential equation solution. Now, that's granted, that's good, but that doesn't look really nice, especially since it involves both sine and cosine. Is there some way to actually simplify this equation? And some of you actually might remember learning a physics formula that doesn't look like that, but they also describe a free oscillation. And we can definitely do that, so let's go ahead and do that. Let's clean up this equation a little bit. The way to clean up this equation a little bit is to do the following. we're going to try to do this. We're going to use C1 and C2 to form a right triangle. And hopefully by doing so allow us to kind of clean up this solution a little bit into something that's nicer. So what I'm going to do is I'm going to define my right triangle. I'm going to let C1 and C2 be the two sides of the triangle. And I'm going to define A to be the hypotenuse and the angle between A and C1 to be alpha. It technically speaking, it doesn't matter which one it is. It's matter little in the formula. I'm just going to call C1 with A instead of C2 with A. But the basic concept is exactly the same. And when that's the case, I can now define the following thing. First of all, I believe that I know A. A will be the square root of C1 squared plus C2 squared. Notice it really doesn't matter because C1 and C2 are two arbitrary constants. Therefore, whatever they come out would be some kind of constant. 2. I noticed that cosine alpha would actually equal to C1 over A, therefore indicate that C1 is actually equal to A cosine alpha. Similarly, sine alpha would equal to C2 over A, and therefore tell me that C2 equal A sine alpha. Now I have what I need to simplify my expression. So our function x of t would just equal to C1, which is A cosine alpha, times cosine radical h over mt, plus A sine alpha, sine radical h over mt. Doesn't we make the expression worse? Well, no, because this is actually a trigonometric identity. And the identity is actually cosine A minus B. So what I'm going to do is combine them together. So first of all, I'm going to factor out an A. And then what I have here would be cosine alpha, cosine radical h over mt, plus A, no A, because I factored it out, sine alpha, sine of radical h over mt. So that is actually the cosine identity for the difference of two angles. So therefore I can now combine them together into this one single trigonometric function cosine. And hopefully that you might recognize this formula from physics, hopefully. In this differential equation, this general solution, there are several things important. So this is basically the general solution to the harmonic oscillation x double prime plus h over m x equal to 0. So therefore now you can actually just simply use this formula to write out the solution to this harmonic oscillation and just simply find A and alpha because h and m actually, now it's correct. H and M are actually given to you. In this equation, the following terms are important. In this equation, A is called the amplitude of the oscillation. And the value radical h over m is sometimes called W sub 0. And this is actually called the angular or circular frequency. And the angle alpha is sometimes called the phase angles. And if you remember learning in Algebra 2, The angular frequency is what sometimes referred to as just frequency, and then the phase angle is sometimes referred to as a horizontal shift or phase shift. All right, now maybe we'll just do a quick example, and then that will be the end of this video. So let's say we're going to try to figure this out. So let's make it easy. We're going to let h equal to m equal to 1. And we're going to let k equal to 0. And f of t equal to 0. Let's try to solve the differential equation. M x double prime plus h or k x prime plus hx equal to f with the initial condition. So the initial condition basically defines the initial displacement and the initial velocity of the piston. So let's just say initial position x of 0 equal to 1 and x prime of 0 equal to 1 also. So let's make it easy. Let's just make everything 1. So how do we do the problem? Well, we can definitely try to just solve the differential equation, but I see no reason why we cannot just use the formula. So here's my formula. Okay, so let's just use the formula. Using this formula indicate that we have f of t equal to 0 and k equal to 0. Now we know h and m are both 1, therefore indicate that x of t would just equal to a cosine t minus alpha. So now all I have to do is just figure out what the initial condition would be and how to solve for the value for a and alpha. So let's do it. So I know x of 0 equal to 1. So therefore tell me that 1 equal to a cosine 0 times 0 minus alpha, which is negative alpha. And if you think about it, cosine of negative alpha is the same as cosine alpha. So I'm going to just say 1 equal to a cosine alpha. X prime of 0 equal to 1. So what is x prime? So x prime is actually equal to negative a sine t minus alpha. So if I plug in 1 equal to negative a sine 0 minus alpha is negative alpha. Now sine is a little different. Sine of negative alpha is actually equal to sine of negative angle is actually equal to negative sine of the same angle. So therefore this actually come out to be 1 equal to negative a sine alpha, so become a sine alpha. So now I just have to solve this system of equation with these two equations. So how do I do that? So the easiest way to do that is the following, is to actually divide them. I'm going to take 1 equal to a sine alpha and divide that equation by 1 equal to a cosine alpha. So to do that, a will cancel out, leave you 1 equal to sine over alpha over cosine alpha, which technically speaking is tangent alpha. And we automatically know that the angle, when you plug in the tangent to give you 1, is pi over 4. Okay, technically speaking, there's another angle, but the other angle is the third quadrant, which is more than 180 degrees, so we're probably not going to consider that angle. Now that we know that, I can now try to find a. So to find a, it's pretty easy. I just do a plug in alpha into either one of this equation. So 1 equal to a cosine pi over 4. Cosine of pi over 4 is rad 2 over 2. So therefore tell me 1 equal to a times rad 2 over 2. So therefore if I divide to this side, a would equal to 2 over rad 2, which is actually rad 2. And so now we have our answer. Our answer is x of t would equal to radical 2 cosine t minus pi over 4. Now, if you want to know what this looked like, remember what you learned in Algebra 2. So here's my t, here's my x. Cosine graph, normally start from the top, but this would have a translation of pi over 4. So we'll go and draw at pi over 4. And then the graph will probably just go something like this. And I actually, pi over 4, it might be closer. And notice this cosine graph would go up and down, up and down, up and down forever, which is exactly what we expect a free oscillation would do. All right, unfortunately, our time is up for this video, so we're going to continue this discussion on tomorrow's video. All right, talk to you guys later. Bye-bye.